In this video, I'm going to do an end-to-end demo looking at genotoxicity analysis. First, I'm going to search for my assay, which is right here. You'll notice that we have both a flat field images directory to correct vignetting, as well as a plate map loaded on this. I'm going to then go into my process screen and load a protocol. This particular protocol is a genotoxicity protocol that has quite a few different steps in this. As this is an older plate, I don't have an image viewer available, though new versions of Endeavor software will produce this. I do have a plate map, and you can see I have 4 different drugs in a dilution series with replicates per row. Here I'm going to look at a topside. A topside is a particular flavor of a DNA damage inducer that induces both double-stranded breaks as well as micronuclei. I'm going to press run for this wellness protocol to demonstrate what each step does for this. But the primary outcomes of this assay are looking at these double-stranded breaks as marked by antibody gamma H2AX, as well as in our nuclear channel, which here is a host stain, looking at these micronuclei, chromosomal fragments that have broken off and have essentially been spat out by the cell. We also have a cell mask stain to segment the cytoplasm of the cell as well. Together, we'll use all 3 of these channels to first identify nucleus, find those gamma H2S punctum marking double-strand breaks, find the cells, make a cytoplasmic mask, then find micronuclei in that cytoplasm mask. Then we'll ratio gamma H2AX as well as micronuclei on a per nucleus basis, giving us an output normalized to cell count. So my first step, we're going to look at the host stain. And here we're going to mask nuclei. So this is using our deep neural net. So the reason why I'm using a deep neural net here is because I first use template matchup to find the cells, and then the fast deep neural net comes in just in where these squares are. And the reasoning behind that is I want to identify these micronuclei. So if I used a thresholding-based methodology, I would segment these micronuclei as well as the rest of the nucleus, whereas this deep neural net has been trained on just images of the nuclei here. So this gets me cell count as well as the segmentation mask. Within this segmentation mask, I'm now going to look for my gamma H2S puncta. There's quite a bit of these puncta, so I'm only going to try to find these bright ones here. Again, we're going to use template match using a small template size because these particular double-strand breaks manifest as very small puncta. They're somewhere between a micron and a half in size and about 3/4 of a micron in size. So now I can see how well that particular step did. So we're first finding these, which did quite a good job of doing that. And then we're going to go ahead and segment those. This segmentation allows me to measure intensity in channel 2, as well as morphology. If I wished, I could specify exactly which measurements I wanted done here. So now we have a count and segmentation of our puncta, as well as a count and segmentation of our nuclei. We're now going to use this channel 4 to find those cells. What we're going to do here is we're going to use those detected nuclei that we found in our first step, look at an area around that for the cell. Indeed, we're able to segment the cellular area quite well. Now, this is not an object-based mask. We're just segmenting whether it's something cell or not cell, because all I'm going to use this mask for is to identify the cytoplasm, which is what we're going to do in this next step. So this next step uses mask math. So basically we're saying use subtract nuclei from our cellular mask, and that's going to give us our cytoplasm mask. And again, this is a population-based metric. So we only care about this to get this cytoplasm to be the area in which we look for these micronuclei, which is what we're going to do in this next step. So using that cytoplasm step, we're going to look in this host channel. So basically just in that one mask, we're going to look in this DNA channel. essentially for these little micronuclei. So what these are when chromosomal fragments break off due to DNA damage. These are much larger than our gamma H2X, so we're going to use an appropriately large template to find these. So now I'm going to turn off that and then turn on my identification. So as you'll notice, we're able to find these small fragments. What we're missing is these very large breaks here. And that is part of the difficulty of a template match, is that if there's an object larger than the given template, it will not be able to find those. So if we wanted to, we could set up a larger template that would find these very large bricks. I'm pretty happy with its ability to find, as well as segment, those micronuclei. Finally, in our last two steps, we're going to create a ratioing puncta count to the total number of nuclei. This will get a readout that's normalized to nuclear count, which by proxy is then normalized per cell count. Another thing to note is that I'm also pre-processing these data. So this is going to flat field connect them. And then that will be able to go through and use intensity corrected data, which is more accurate to analyze all these images. Another thing to note is I'm linking objects here. So these links are both implicitly created by the fact that I'm using nuclei and cells in steps. So basically nuclei, cells, and cytoplasm are all being used to find one another. Therefore, they're implicitly linked. And I can define those links here. I also have made custom links, which I can add here. And that is basically saying, using bounding box overlap, I'm going to associate one measurement object with another. This allows me to summarize measurements based on those, as well as make measurements based on the whole cell and all its representative parts. Since I'm now happy with this analysis, I'm going to run it.